Hi, I am Dmitry and the topic of my presentation is development of physics-informed neural networks for solving partial differential equations. Partial differential equations are used in modeling physical phenomena such as heat conduction, diffusion, hydrodynamics, and others. Physics-informed neural networks, or PINs for short, are feed-forward neural networks that incorporate the laws of physics expressed as differential equations directly into the training process. These neural networks have gained popularity in recent years. The goal of this work is to analyze and compare the effectiveness of PINs in solving two-dimensional stationary and non-stationary problems, including ones with Robin boundary conditions and non-rectangular domain, and to develop neural network architecture for these types of tasks for which efficiently has not been sufficiently studied. In this figure you can see the architecture of a pin for solving Poisson's equation. The network takes as an input the variables on which the equation depends, processes them through hidden layers, and outputs an approximate value U hat. The necessary derivatives are computed and substituted into the equation, along with the boundary and initial conditions if present. Based on this data, the loss is calculated. Then an optimization algorithm, using the derivatives of the loss function, it updates the network's weights, and the forward pass is repeated until a specified condition on the loss function is met. The PIN algorithm consists of the following steps: input data for domain, equation, and boundary condition. Define training samples for the equation and boundary conditions. Incorporate the computation of the necessary derivatives for the equations within the neural network. Define the loss function for the equation and conditions. And train the PIN to obtain an approximate solution by minimizing the loss function. The loss function is computed as a weighted sum of mean-square errors of the equation approximation, the boundary conditions, and the initial conditions. Here are pros of these methods. PIN allows you to easily modify the differential equations and boundary conditions, which facilitates adaptation to new problems. It can work with variety of geometric structures without the need for a mesh, which simplifies the modeling of complex geometries. It integrates a prior knowledge of physical laws into the learning process, which increases the accuracy of modeling. It can be applied to high-dimensional problems, and PINs can use modern optimization and learning techniques to improve the ability to generalize and adapt. Cons like other optimization methods based on gradient descent, it can stuck in local minima, which leads to incorrect or incomplete solutions to problems. The optimal choice of hyperparameters for pins, such as network architecture and learning rate, can be complex, requiring significant resources for experimentation. The convergence of pins to optimal solution is not guaranteed, especially in complex problems with many local minima. Pins, like other neural network methods, can be computationally intensive, especially for large or high-dimensional problems, which can be a limitation for some applications. For implementation of PIN, Python TensorFlow library was used, and neural network was trained on GPU NVIDIA RTX 3080 Ti laptop. For FEM, Phoenix library was used. Let's consider Laplace problem with Dirichlet-Neyman and Robin boundary conditions. The neural network has three layers with 10 neurons each. For training, 11 nodes in each axis were chosen. Here we can see the loss function for the problem and approximate solution of it, obtained after 13,900 epochs over 3 minutes and 49 seconds. Approximate solution obtained by FEM and PIN is shown on left and right boundary, where we set Neyman and Robin boundary conditions. Also, normal derivative of U obtained using PIN are shown, which on the left plot is equal to 0 and on the right plot is equal to U. On these plots, approximate solutions obtained by FEM and PIN are shown on top and bottom boundaries, where we set 0 and 1 Dirichlet boundary conditions. A PIN solution has approximately 2.9% relative error in L-infinity norm. It is compared with FEM solution on 10 by 10 grid. The second problem is non-stationary heat conduction problem with zero Dirichlet boundary conditions, and initial condition is set by 11th equation. Neural network for this problem has 3 layers with 13 neurons each, and for training 25 nodes were chosen for each axis. Here we can see the loss function for the problem and approximate solution of it obtained after about 12,500 epochs over 5 minutes and 42 seconds. For this problem, analytical solution is known, so on plots we have approximate solution obtained by PIN, FEM, and analytical solution at initial time on the left and at final time on the right. On these plots we have approximate solution obtained by PIN and FEM and analytical solution on left and right boundary along time axis. From this table, as you can see, PIN after training has relative error in L-infinity norm about 1.7% when comparing to FEM and analytical solution. The last is the Dirichlet problem in doubly connected region with Dirichlet conditions. Here we have 3 layers with 30 neurons each. On each boundary 50 nodes were chosen and 500 internal nodes were chosen for training. Here we can see the loss function for the problem and the approximate solution of it, obtained after about 10,500 epochs over 4 minutes and 20 seconds. On these plots we have approximate solutions obtained by PIN, FEM, and analytical on inner and outer boundaries. Also, PIN solution with different number of epochs are shown as dashed green and blue lines. As you can see, they converge to exact solution from more training epochs. As you can see from this table, relative errors decrease the longer we train the neural network. And after about 10,500 epochs, it is about 2.3%. The application of physics-informed neural networks with developed architecture has proven to be an effective method for solving most of the considered problems with Robin conditions in doubly connected domains and non-stationary problems, since the networks are trained directly from the differential equations, ensuring satisfactory accuracy even with a limited training dataset. However, they require significant computational resources and training time. Despite these limitations, the use of pins for partial differential equations opens new opportunities for modeling and analyzing physical systems. Since the pin successfully solved the problems presented in this work, there is a potential for its application to more complex problems, and further research should focus on reducing training time. Here is a list of main sources used. By following a QR code, you can find a full list of references. Thank you for your attention. Do you have any questions?